Okay, so let's do some of these examples together. So when I go to my y is equal to screen, my function screen, I want to make sure that I enter in my fraction 1 divided by 2, and that's going to be to that, and I want you to make sure that you see that this needs to be protected by the parentheses. So that's going to be to the parentheses x minus 3 power. Now what's interesting here, I can make a prediction on where this graph is going to go. This is my h value, so I'm going to say that this graph is going to be shifted this way 3. So when I look at my graph, I see 1/2, and instead of cutting the axis and being here, it's shifted this way. Let's talk about why. First of all, my b is between 0 and 1, which means it's going to be exponential decay. So we'll go ahead and we can fill that one out immediately. If I want these exact values, the smartest, quickest thing is to go to the table of values. So go ahead and position your calculator so that 0 is right in the middle. Then it makes it easy for you to see -2, -1, 0, 1, and 2. I know anything to the 0 power is equal to 1, but check out what ends up happening when this graph gets shifted over. I end up with a surprising 8, and then a 4, and then a 2. Notice I don't get a 0 power until I have a 3 minus 3, which is going to end up giving me that value. So your smartest thing that you can do for these equations is enter in the equation to the calculator and take a look at the table of values. Once you have that table of values, 8, 4, you can get a picture of where that graph is going to be. Now in this case, it might have helped us a little bit more to have a 3 here, because then I would have put 3 minus 3 is equal to 0. Anything to the 0 power is 1. And then, of course, my greater numbers, when I put in, are going to continue to have this exponential decay equation get closer and closer, but never cross my axis. Okay, let's talk about my transformations. So my transformation was that I went to the right 3. We already talked about it, how it's being decay. Of course, my horizontal asymptote is still going to be the horizontal line, y is equal to 0. As far as my domain goes, anything can go in. I'm fine with anything going in, but let's talk about what my range is going to be. My range is going to be anything snuggling up to, but not including 0, all the way up to infinity. And my y-intercept is going to happen at an input of 0, gives me an output of 8. All right, so let's take a look at our next example here. We'll talk first. First of all, I know it's going to be a reflection. I know it's going to be growth. So when we talk about, we can put that down right away. Of course, my graph is going to be a reflection because of that negative. I can tell it's going to be growth, or I can just circle this, because that my base, here's my b, my base is going to be greater than 1. My graph is not going to go left, right, but it is going to go up 2 because of this k value that I have there. So because of that, my horizontal asymptote is not going to be at 0 like this one was. Instead, it's going to be up 2. So my horizontal asymptote is going to be 2 up. So y is equal to 2 is going to be the line it'll approach and never quite reach. Again, my domain, anything can go in, but not necessarily come out. And it'll be interesting to see what happens to our graph when we look at this example. Okay, so we'll go ahead and we'll enter it into the calculator. We have the opposite of 2 to the x power plus 2. Now this plus 2, make sure that we have it not a part of the exponent. So if you have a newer model calculator, you have to arrow out because that plus 2 needs to be down, and you need to see what looks like an exponential growth graph flipped, because that's going to be, it's still growth, it's growing away. That's what that negative sign does to my outputs. All right, so when I go ahead and I enter in my equations I have, or my values on my table, -2 gives me an output of 1.75. -1 gives me an output of 1.5. 0 is 1. 1 is 0. And 2 is -2. So when I go ahead and I put these into the calculator, over 2 and down 2, and I have over 1 up 0, over 0 up 1, and then you'll notice that this part of the graph is going to approach my asymptote, never reach it, and then this part of my graph is going to exponentially fall. So my y-intercept is going to be an input of 0, gives me an output of 1. My range here is going to be from -infinity all the way up to, and it's going to get as close as it can to my horizontal asymptote, but never touch it. That's why we have the curve. All right. So when we look at the next part of this equation, we have, okay, looking at what happens with 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, and 10 to the fifth, and 10 to the sixth. That is what our n is going to be worth. So this is an interesting idea, because what we're talking about here is this is what happens, this equation is what we use when we figure out how to do compound interest. So when you're put money into the bank, you want them to figure out your interest more than once a year. So this equation helps explain why compound interest works the way that it does. I'll give you a minute to fill out this chart and come on back and we'll compare answers. All right, so what we're going to talk about both this week and next week is this crazy number E. So E is an irrational number that mathematicians have discovered. So it's not the same as pi. It has a different value. But if you want to compare it to pi, pi is a little greater than 3. E turns out to be a number that is a little less than 3. It's a number that mathematicians stumbled upon when they were trying to figure out how to make the most money that they could. So they used this formula, which we're going to talk about in a couple weeks when we talk about compounding interest. So our compound interest formula, if you notice, has two parts to it that end up changing, whether it has n as a divisor or n as an exponent. And the cool thing about this is if you played with this and entered this into your calculator, when you had 10, 1 plus 1/10 to the 10th power, you ended up with that. When you had 1 plus 1 divided by 100 to the 100th power, you ended up with a larger number. When you added 1,000 in for n, your number got larger. So I was able to just write the first two decimal places. But once I reached putting 1,000, 10,000, 100,000, and 1,000,000, notice my number started to be so incredibly similar until I got to the point of where it wasn't different enough until I continued going. So here's my work on the calculator. You can see that I did 1 plus 1 divided by 10 to the, here I did the 5th power, here's the 6th power. And that's going to be raised to that 10 to that exponent. Hey, here's a calculator shortcut for you. Do you see this button here that says entry in blue? If you press second and entry, it'll give what you last typed into your screen. Then you can go through and look and change that exponent. So once I typed it in once, I went through and changed it each time. And that's how I was able to get closer and closer. So E has a value that's about 2.718. We can continue on and memorize infinite, try to memorize many digits of it. It is actually an infinite value in the decimal places because it's an irrational number. It goes on forever and ever. It gets closer and closer to 2.7182. When we talk about E, that's the value that we get. And mathematicians discovered this when they were working with compound interest. So E is an irrational number, which is approximately 2.718. E can be found at the calculator, so your calculator has this number in it already. If you look at your division symbol, on mine it's blue, it might be yellow on yours, but that is our number E. When we're graphing exponential functions that have E as the base, we're going to use that key and all of our other properties remain the same. Okay, let's take a look at the back. Of course, here we have y is equal to e to the x. So we can go to our, make sure we have this down here, e to the x, and we can look at y is equal to, we can go right to what we just learned. There's e to the x power. We use this number a lot, just like we use pi a lot for circles. E we use when we're talking about compound interest, when we're talking about solving exponential equations. And next we're going to learn about the inverses of those, a funny term called logs. But we can go to the table of values. Now, of course, everything is fractions except for the one thing that we always know is true. Anything to the 0 power is 1. We know that e to the first power is 2.7. That's good enough for us. E squared would be 7.3. If we're going to divide by e, remember a negative exponent means division. 0.36. And if we're going to divide by e squared, that's going to give us 0.13. When we go to look at the graph of e, it looks very similar to all of the other exponential graphs that we've had. Anything to the 0 power is 1. Our first power takes us short of 3, and our second power takes us a little over 7. So my curve continues to grow exponentially. And then on the negative exponent side, it's going to approach the asymptote, which of course is y is equal to 0. It is definitely growth. My horizontal asymptote is y is equal to 0. Anything can go into my graph, but only those values greater than 0 on up to infinity are going to come out. When we're talking about the transformations for E, we can talk about the same exact things. I know right away this is going to be a reflection. I know it's going to be a stretch of 4. I know it's going to be shifted to the right 3, and I know that my graph is going to go up 2. Just by looking at those equations, I can tell what's going to happen to that graph. Okay, let's go ahead and type that in and see how it looks into our calculator. So we'll go ahead and we'll say the opposite of 4 times e to that, and don't forget to use your parentheses for your exponent, and then plus 2. If you have an older calculator, make sure you arrow out for the plus 2. So we can take a look at this graph, and it makes sense to us that it's reflected, first of all. It makes sense to us that it's moved to the right 3, it's moved up 2. And it's hard to tell with these graphs, but it is a stretch. It is getting higher, or in this case, because it's reflection, lower, faster. So we can go ahead and just literally get these values from the calculator. 1.92, 1.8, 1.4, 0.5. It might be worth having this one there just so we can get an accurate picture of where the graph is. So we'll go over 3 and down 2, over 2 and down 1/2, and over 1 and down, or over 2, this is supposed to be up 1/2, and over 1 up 1.5-ish, over 0, 1.8, -1 is going to be 1.92. So this is going to get, pretend like this is not one that we want to see, not that one. Here is our asymptote, and we can see that our graph approaches that, but then gets very steep as it goes this way. Our horizontal asymptote is y is equal to 2, because this whole graph was bumped up 2. It is growth because it's moving away from the axis. My domain is all real numbers. My range is going to be -infinity up to, but not including my asymptote. My y-intercept is going to be when 0 goes in, 1.8 came out. When we talk about our increasing and decreasing interval, we're talking about moving from left to right. So this graph does not increase at all. The whole time it's getting, my output values are getting smaller and smaller, which means it is decreasing among its entire interval, from -infinity to +infinity. When we talk about our end behavior, as x approaches -infinity, my output is going to approach my asymptote. As x approaches +infinity, my output is going to approach infinity. All right, so let's talk about these quick hints at the bottom. Quick hints. Fill in the blank. For the function, as x approaches infinity, what is my output approach? So we can take a look at this for a minute, because this is positive and this is, so if this is positive, I know I don't have a reflection. This is decay, so I know my graph is going to be one of these. This graph is going to be shifted to the left 1. It's going to be shifted up 3, which means my asymptote is going to be shifted up 3. So as x approaches +infinity, my output is going to approach 3. All right, let's take a look at 8. What is the asymptote of that function? It has a negative, so we have a reflection. So we take a graph of E that is normally like this, and we're going to reflect it. So it's going to be like this, where y is equal to 0, is going to be our asymptote. Whether we move it left or right, it doesn't matter. This one is going to go to the left 1. This is what matters. My asymptote is going to come down 2. So my asymptote for this one is definitely going to be y is equal to -2. All right, let's look here. What is the 0 of this function? So the 0 means what value gives you an output of 0? Where does this cross the y-axis, cross the x-axis? Y to the x, or 9 to the x minus 243. If I go to solve for that, 243 is equal to 9 to the x. 9 to what power is 243? We can kind of cheat and solve this one by taking 9 to the x power, going to our table of values. Do you see 243 ever? Nope, me neither. So because we don't see it, let's go ahead and look at the graph, because what we're caring about is where does it hit the y-axis, the 0. Oh, we have to put the whole equation in. 9 to the x minus 243. That's better. And then, of course, we're not going to be able to see it because it's going to be way, well, the curve is going to be way down here at -243, but we can see this value. So let's go ahead and do second calc. Let's find the 0. We'll say our left bound is going to be, let's see, where's our x value? Try to get our x up. We missed it. So if you look here, x, our output's negative here. At about 2.5 is going to be our 0 of the function is going to be a 2.5 goes in and the 0 comes out. You might not want to write yourself a note that we graphed for that one, and then we used second calc to solve. All right. Over what interval is the function increasing? So we'll go ahead and we'll take a look at that one on the graphing calculator too. So we'll go ahead and enter that into the graphing calculator, -2, parentheses, 1 divided by 2, end of parens, 2 the parens, x plus 1 power, and then plus 4. So when I look at my graph, there's my equation. If I want to know where it's increasing, it's always increasing. So we're going to call that -infinity to +infinity. All right, good job on these practice problems.